Hello everyone, how are you doing? Welcome back to the classroom of CMPT 459 Data Mining. In the last 2 weeks, we have an introduction to the course and we also discuss how to get to know your data. Now you have some ideas about the basic data types and basic types of attributes and how to use the basic statistics to describe your data. And also you know some techniques to visualize your data. Now we can start to work with data. So starting from today, we'll talk about how to analyze the data. As the first step in the whole KDD process, we need to prepare our data. We need to pre-process our data. This is the topic today for data preprocessing. There are several major tasks in data preprocessing, including the processing data before an analytic task, to improve the data quality, to transform data to facilitate the target task. We need to do data cleaning. Essentially, we need to handle missing data. We need to smooth noisy data. We need to identify or remove outliers and remove inconsistencies hidden in the data. You may have data from multiple sources. For example, some data may be from your relational database, some data may be from your IoT devices, and some data may be from a social network. Then you need to integrate multiple databases, multiple data sources, so that you can have one united view on the data. You have much of the data. There could be some redundancy. There could be some parts of the data that you do not really need. So you need to do the data reduction. When we say data reduction, these may include dimensionality reduction. You reduce the number of dimensions, you remove those attributes you don't need, or the numerosity reduction. And also, when the data set is too big, and to facilitate handling, transferring, and also the communication, you may want to compress the data. So this is data compression. The raw data may not be convenient, so you may want to do data transformation and data discretization. Through data transformation and data discretization, we can normalize the data so that the analytic results are more reliable. And we may also construct a concept hierarchy so that data can be better understood. So in this lecture, we will cover all those topics to give you some basic ideas about data preprocessing. And at the end of this lecture, you should be able to start your data exploration and preprocessing by your own using some tools and on some large data sets. When we talk about data, one important issue is the data quality. Whether the data is accurate, whether the data is complete, whether the data is consistent between your observation and also the data reflects, or among different sources. And of course, we want data to be updated, to be timely, so that we can get the latest observations. Data is often large, so that one big issue is whether you can trust your data. Whether you think that your data make good sense, whether your data are accurate, are correct. So this is the trustability or believability. And also, given a large, complex data set, it is often hard to understand and hard to interpret to the end users what are happening within the data. So whether the data can have good interpretability, easy to understand, easy to consume is another important quality measures. Those are the data quality measures, as I just mentioned: accuracy, completeness, consistency, timeliness, believability, and interpretability. Let's start from data cleaning. As we all know, the real world data is more often than not dirty. Why we say it's dirty? Because there are many factors that we cannot control may have noisy effect into the data. For example, there could be lots of potentially incorrect data. There could be some instrument faulty, or there could be human or computer errors. And even the network transmission may introduce transmission errors. Those errors, those incorrect data may lead to the dataset to be incomplete, meaning some attribute values may be missing, may be lacking, and some certain attributes of interest may not be even collected or contained only some aggregated data. For example, in many tables about customers, you may have the occupation attribute missing. And data can be noisy. It may contain noise, error, or outliers. For example, there could be some input error. When we key in a number, we just by chance make a mistake. And also it may be some inconsistency within the data. For example, there could be some discrepancies in codes or names. For example, the age may not be consistent with the date of birth. And also there could be different key numbers for rating. For example, we have the letter grade A, B, C, D, but for some people they may key in the wrong input, may use the number, say 1, 2, 3, and so on. And also there could be some conventional inconsistency. For example, like when we use the date, and when we want to collect the birth date, and then if one doesn't want to release the private information, they may just randomly pick a value, for example, January 1st. So look at the customer database, you may find a large number of people have January 1st as their birthday. So in order to solve those issues in data, we need to do data cleaning. Data cleaning essentially is the process of detecting and correcting the corrupt or inaccurate records from data. It has to handle missing data, it has to smooth data to some extent. We'll explain the details next. First, let's look at how to handle incomplete data or missing data. Data are not always available. For example, there are maybe many tuples that have no recorded value for several attributes, such as the customer income in sales data. Those may be due to privacy concerns, may be due to the data collection capability concerns. There could be multiple reasons for one data item missing. Maybe the equipment malfunction, the equipment just missed that data point. There could be some inconsistency with other recorded data, and thus the data is deleted by someone else. The data may be not entered properly due to some misunderstanding. For example, if an operator doesn't really understand the requirement for one data field, she or he may not even bother to enter data value there. Some data type may also have the problem, say that some data may not be considered important at the time of entry, but later on we find the data is very important and very useful. Or we may not register the history or change of the data so that we don't have the latest data about one value. We may have only very outdated data. So we need to infer or the missing data. How to handle the missing data? There are several approaches from simple to sophisticated. They have completely different implications to our data analytics. The first approach, of course, is the simplest one, is that we can just ignore the tuple, ignore the records that with missing data. Obviously, this approach is not effective because when the percentage of missing data per attribute is high, then you run out of enough data for your data analysis. The second approach is that let's fill in the missing data manually. If we can find some dedicated domain experts, they check those data records one by one, and then once they see one missing data, they try to fill in the appropriate value there. Well, the technical quality could be high, but this is a tedious work, a lot of work, and in many situations, if the data set is large, such a manual approach may not be even feasible because it is just too costly in both time and in the human labor. So that comes to the third category of approaches which are frequently used. That is, we try to come up with some ways to fill in those missing data automatically. But when we say automatically, there's still multiple choices here. The first choice is that we can use a global constant. For example, we always fill in a value, say unknown or void, as a new class. This makes the data literally complete, no missing data. But at the same time, the semantic, the meaning of this unknown becomes really unknown. Another way is that for any attribute value that is missing, we just use the mean of the whole attribute to fill it in. So this will make the data sort of like shrinking to the central point of the attribute. Well, how well this method worked for the data analytics is unknown, and it may, mix some capability in our data analytics later. And if the data tuples belong to multiple classes, then a smarter idea is that we look at the attribute mean for all the tuples, all the samples belonging to the same class. And then the same class, when we see an attribute value missing here, we use this class-wise average as the filled in. That may serve better because the rationale behind this is that all the tuples belonging to the same class may have a better chance to be similar to each other. If we want to go even further to provide even better quality, then another approach is that we can try to find the most probable value, which is an inference-based value, such as we use some Bayesian classifier or decision tree or any classification model to predict what should be the value there. Then the advantage is that those values could be fitting the data very well. But on the other hand, the models you use to make the prediction may also have a strong footprint on your later data analytics. Now, let's use disguised missing data as an example to understand how missing data can be treated. Disguised missing data is the missing data entries that are not explicitly represented as such, but instead appear as a potentially valid data values. Let me give you some concrete example to understand this concept. Suppose you are asked to enter the entries in a web form. For example, you need to register yourself in, say, online e-commerce form. And some attribute values you don't really want to provide an accurate value, but the system doesn't let you go if you don't provide something. For example, in some cases, people don't want to release the states they're staying, or they don't want to give the exact date of birth. In such a case, one idea people often go with is that they just randomly pick a value and just try to get the form filled so that they can go to the next step. In such a case, indeed, they do not really randomly pick a value, and due to the convenience, they will probably may pick the first value in the list, for example, such as people quite often use Alabama as their state because when you click the link, Alabama shows up as the first. Using the data collected as such, one problem is that the business decision may be wrong. For example, if you look at the data, you see, oh, there's so many customers in Alabama. Then you may make a wrong decision to say we should even open more branches in Alabama. And also, another example is that the data may give you a lot of wrong message. For example, if you collect the data, people do not really input their blood pressure properly. Many of them may even just key in a value of 0. Then you have a trouble. You say, well, why there so many customers have 0 blood pressure? There are different types of disguised missing data. One is that we randomly choose a valid value as disguise. Another is that a small number of values are chosen as disguise heavily. For example, if we have the number of customers, we look at the how many of them may use disguise missing value. In this figure, it shows, well, if this disguise missing values are randomly distributed among all the valid choices, then this is a randomly choose valid data. And in this case, many of the customers use Alabama as the disguise value. Then the Alabama becomes unproportional high in number of customers, and thus the disguise missing value indeed is focused on Alabama. Then the problem of cleaning disguise missing value becomes the following. We are given a table T with attributes set A and an integer K. K typically can be a very small number like 1, 2, or 3. For each attribute AI in this A, we want to identify up to K candidates that are frequently used as disguise value. Finding the disguise value is important because once you identify those suspect disguise values, then you can pay attention in your later analytics and try to avoid or compensate any overestimate or ill effect caused by those missing data, disguised missing data. How to do that? The major idea to combat disguise missing data are based on two observations. In the first observation, if we assume that there are some frequently used disguises in such missing data, then we will see a small number of values are frequently used as the disguises. The second observation is that, well, those data are missing at random, meaning the missing data are often distributed randomly. So the idea here is that we try to identify a random subset of the whole database that using some these disguised value. If for one attribute, I can identify a subset of this attribute that is a uniform the distribution is similar to the whole data set, then likely this attribute value is used as a disguise. So the general framework is the following. For each attribute A, what we can do is that for each frequent value V in this A, we compute the maximum embedded unbiased sample contained in TV. That is, among all the tuples having value V, we try to extract a largest subset that mimic the global distribution on all the other attributes as the whole data set. Then this subset serves as the maximum embedded unbiased sample. And if this maximum embedded unbiased sample is large, that means this attribute V may have a large likelihood of being the disguise. So we return the K values with the best in both quality and size of the embedded unbiased sample. Now let's look at noisy data. We said noise is the random error or variance in a measured variable. So there could be several causes of noise. For example, we may have 4D data collection entrapments, so that those entrapments introduce incorrect attribute values. We may have data entry problems. For example, when we key in our telephone numbers, we may make a mistake on some numbers, or we switch the order. We may have data transmission problems, so that the data is not transmitted correctly. We may have some technology limitation. We cannot get the data in a fine granularity as we wish. We may have inconsistency in name convention, so that the data contains in different conventions, so that they are not consistent with each other. There may be also some other data problems lead to noisy data. For example, we may have duplicate records, we may have incomplete data, we may have inconsistent data. We need to deal with such noise in data. How to handle noisy data? There are several approaches. First, we can do binning. Here, binning means that we can first sort data and partition data into bins. The bins can be organized in the equal frequency style, meaning each bin contains the same number of data records. Then, one can smooth by bin means, instead of looking at the specific data values, or smoothed by bin median, or smoothed by bin boundaries, and so on. Binning essentially is trying to use larger granularity to replace the finer granularity data, so that the data can be more smoothie and can avoid some up and down data variance. Another way is to do regression. Essentially, you can try to fit the data into regression functions so that the data can be smooth. Or you can do data clustering. Clustering itself is a data mining technique. Essentially, as we introduced in the first lecture, clustering tries to identify the groups of data that are similar to each other, and so that the data in different groups are very different from each other. So by identifying clusters, you can remove those outliers, which are the data points that are far away from any major groups. After removing such outliers, the data can become more, hopefully cleaner. Or we can do some semi-supervised approach. The idea is that we can combine the computer and human inspection together. We can detect the suspicious values, such as using the outlier detection approach we just described, and then we can track by human being to identify and to judge whether those suspects are really outliers and whether they should be removed from our consideration. So data cleaning itself is the whole process. We need to do the data discrepancy detection. We can use the metadata to help. For example, the domain knowledge, the range, the dependency, and the distribution. And we can check the field overloading. We can check the uniqueness rule, the consecutive rule, and the null rule, so that we know which data items are out of range, out of our domain specification. We may even use some commercial tools to do that. For example, we can use data scrubbing, meaning we use simple domain knowledge such as the postcode, spell check to detect the errors and make corrections. For example, if in a data set someone key in a postcode that doesn't exist, then we know there's noisy data and should be clean. Or in a data set, if we find the customers in one area, in one postcode area, the number is even larger than some government statistics, then there must be something wrong with data entry in that area. We can also do data auditing, meaning by analyzing data to discover the rules and relationships to detect any violation. For example, we can conduct a correlation and clustering to find outliers. We can do data migration and integration. Essentially is that you can allow the transformation to be specified using data migration tools to make sure the migration follows good data specification. Or we can use the data ETL tools, meaning the extraction, transformation, and loading tools to allow users to specify the transformations through a graphical user interface. And typically, we can do data cleaning in a two-step process, iteratively. And the first is that you use the automatic tools to identify possible suspects and do the transformation. And in the second step, you introduce the human interaction so that the domain knowledge can be filled into this whole process. In order to do this, we need to look at the some specific issues here. One is a data integration. Data integration is to combine data from multiple sources into a coherent store. When we say integration, indeed, it may contain multiple tasks. The first task is often the schema integration, meaning we want to, at the schema level, at the metadata level, we can connect different sources. For example, in one table, we may see an attribute called customer ID, and on another table, we may see another attribute called customer number. And from the domain knowledge, we may know these two attributes indeed are related, and not only related, they should refer to the same information. So we need to build this connection. Second, we can do entity identification. We may see different data objects referring to the same real-world entity. Entity identification tries to identify real-world entities from multiple data sources. For example, we may have the same person, but calling them in different ways. Bill Clinton is the same as William Clinton. So we need to link these two data records together, referring to the same physical real-world entity. Third, we may want to detect and resolve data value conflicts. For example, for the same real-world entity, the attribute values from different sources may be different. There could be many reasons for that. For example, the data may be represented in different format, different ways, or they may use different scales. For example, for the distance, in some situation we may measure that in feet, and in some other situations we may measure that in meter. In data integration, we will have to handle the redundancy, because redundant data may occur often when integration happens to multiple databases. There are two situations here. One is object identification. The same attribute or the same object may have different names in different databases. We need to identify those different names so that and link them together to resolve these object identification redundancy. Another situation is the derivable data. One attribute may be derived from another attribute. For example, we may have the data about the sales in every month, and we may have another attribute to say what's the annual average sales or annual total sales. Then, of course, the annual total sales should be derivable from the 12 attributes of the sales in all the months. Then we need to identify such redundancy. Redundant attributes may be able to be detected using correlation analysis and covariance analysis, which will be introduced later. And if we can carefully integrate the data from multiple sources, this may help to reduce or avoid redundancy and inconsistency and improve the data quality. The improvement of data quality can later help to improve the data mining quality and also the data mining speed, because we do not need to handle those redundant data. In order to detect redundant attributes, you need to do correlation analysis. Let's start from the correlation analysis for categorical data. One popularly used method is called chi-square test. Chi-square test is calculated as shown in this formula. The chi-square is the sum of the difference between the observed attribute frequency, value frequency, minus the expected frequency, the square, and divided by the expectation. We sum them up on all the possible values here. So chi-square test essentially is a statistical test. The non-hypothesis is that the two distributions are independent. The cells that attribute the most to the chi-square value are those whose actual count is very different, either very much higher or very much lower than the expected count. And later I will use an example to show you how to do this. And the larger the chi-square value, the more accumulated things here, then the more likely the variables are related, because we say if the this expectation is calculated using the independence assumption. So if the observed value, observed frequency is much different from the expectation, meaning the two attributes are indeed not independent. They are more correlated. Here, one thing we need to keep in mind is that correlation is not causality. Meaning, if we see two attributes correlated, it doesn't mean one attribute is the reason or is the cause of the other. For example, the number of hospitals and the number of car thefts in a city are correlated, but both are causally linked to the third variable, for example, population. Let's look at one concrete example here. Suppose we have two variables, say two attributes, say like science fiction and not like science fiction. And they also have the values, say play chess and not play chess. Then suppose we have 250 cases they like science fiction and they also play chess. And we have 200 like science fiction and not play chess. And 50 not like science fiction but play chess, and 1,000 not play chess and not like science fiction. We sum them up, we know we have 300 players of chess players in total, and we have 1,200 in total here. And we have 450 here, we have 1,050 here, okay? So if these two variables are independent, then the chance of someone like science fiction and play chess would be 90 over 300. This is calculated by, should be the ratio between these two, okay? So essentially is 450 take the ratio between these two, so that you get the 1/5 of this. Okay. Yeah. So this 90 is calculated as this 450 divided by the total is 1,500, but this column has 300 in total, so the share here should be 90. And because this 90, so similarly we have these 210, and because in total this row should be 450, we have 90 here, so we have 360 here. And this has 840 here to make up the sum of 1,050. So those are the expectation. Then we can calculate the chi-square as follows. following the formula we just see here. So for each one, we use the observed value minus the expectation and take the square divided by the expectation. We sum them up, and this is the total is 507.93. And then we need to look at the confidence level. For example, at the confidence level of 0.001, and then if you look up the table from any statistical tables, then you will see we can reject the null hypothesis, meaning those two variables are not independent. If we need to handle a random variable, which is a numerical variable, then we know that the variance of a random variable x can provide a measure of how much the value of x deviates from the mean of the variable x. So the variance can be calculated as in this way, and we explained this in the previous lecture on how to know the data, getting to know the data. Okay. Then, if we have two numerical variables, indeed we can calculate the covariance. The covariance between two variables x1 and x2 is the expectation of x1 minus mu1, x2 minus mu2. The central idea here is indeed very simple. If the two variables x1 and x2 are correlated, then whenever we see x1 is over the expectation, x2 should have a good chance also over the expectation. If x1 is less than the expectation, x2 is also have a chance to less the expectation. Therefore, if x1 and x2 are correlated, then the sigma 1, 2, the covariance of the two variables should be large. On the other hand, if x1 and x2 are independent, that means the sign and also the value of x1 minus the mu1, which is the mean of x1, and the difference between x2 minus mu2 would be independent. Therefore, the sum, the expectation, should be close to 0. So this is the idea behind the covariance of two variables. And we know if we have the covariance is over 0, then these two are positively covariant. Okay. If x1 and x2 are independent, then these sigma 1, 2 should be close to 0. Okay. However, we need to know one thing. If this sigma 1, 2 is close to 0, but still x1, x2 may not be completely independent. There's still some situations, indeed there's some relationship between this x1 and x2. How to calculate the covariance? Let me give you one example. Suppose we have two stocks, x1 and x2, have the following values in 1 week. x1 takes 2, x2 takes 5, x1 3, x2 8, x1 5, x2 10, x1 4, x2 11, x1 6, and x2 14. And we want to see whether the two stocks are correlated. We use the covariance formula. So we have the first, the expectation of x1 is 2 plus 3 plus 5 plus 4 plus 6. The sum divided by 5, which is 4. And the expectation of x2 is 5 plus 8 plus 10 plus 11 plus 14. Also divided by 2 is 9.6. Then we can calculate the sigma 1, 2 as the 2 minus 4 times 5 minus 9.6 plus 3 minus 4 times 8 minus 9.6 and so on. So you can get the covariance to be 4. And because the covariance is positive, that means x1 and x2 may rise together. We know we can calculate the covariance, but covariance, the scale may be affected by the variance. Therefore, to measure the correlation between two numerical variables, one idea is that we can normalize the covariance by the standard variance, and then we can calculate using this rho 1, 2 formula like this. And we can also use a sample for two attributes x1 and x2 to estimate the correlation between two attributes. If this rho 1, 2 is over 0, then A and B, these two attributes, are positively correlated. If rho 1, 2 is 0, under the assumption that we discussed in the covariance, then we say the two attributes are independent. And if rho 1, 2 is negative, then they're negatively correlated. Indeed, we may also form a covariance matrix if we have multiple variables and we want to observe the relationship among those attributes. Essentially, we have a data matrix here. Each row is a record and each column is an attribute. And then we can form a D times D matrix where the diagonal are those variance of those variance of those attributes. And then for the cell ij is the covariance of attribute I and attribute j. So we will stop here for the first part of data preprocessing. We'll continue next time. Take care. Bye-bye.